Have you ever wondered why the ground beneath our feet is never really, truly still? Today, we're going to connect the dots between the basic laws of physics and the incredible power of volcanoes and earthquakes. And what's wild is, it turns out, the same principles that make your coffee go cold are what make entire continents move. Let's dive in.
Think about it. You see footage of a volcano erupting, or maybe you've even felt the ground shake in an earthquake. What's actually going on down there? Well, these aren't just random events. They're all symptoms, the visible signs of a gigantic heat engine churning away deep inside our planet.
Now, I'm about to say a word that might give you some bad flashbacks to physics class. Thermodynamics. I know. It sounds complicated and, let's be honest, kind of boring. But you gotta stick with me here, because those exact rules are the secret key to unlocking why our planet is so incredibly active and alive. All right, so before we get into the nuts and bolts of the engine, let's first take a look at the results. Let's start with the symptoms, all the dramatic stuff we can actually see happening right on the surface.
So what you're seeing here is something called a subduction zone. It's basically a slow-motion crash where one massive piece of Earth's crust, a tectonic plate, is getting forced down underneath another one. This process is a volcano-making machine, and it's why you see so much geological drama, volcanoes, earthquakes, you name it, concentrated along the edges of these plates, like in the famous Ring of Fire that circles the Pacific.
So that begs the question, right? What in the world has enough power to shove these continent-sized slabs of rock around? What's the fuel for this planetary engine? The answer is actually incredibly simple. It's all about heat. Let's follow the energy. So if the planet's core is super hot, how does all that heat get out?
Well, in the world of physics, there are really only three ways for heat to get from one place to another. Our planet uses all of them. Let's do a quick rundown of conduction, convection, and radiation.
First up, you've got conduction. This one's easy. It's just heat transfer through direct touch. You know how the handle of a hot pan gets warm? That's conduction. In the same way, heat slowly works its way through the solid rock of the Earth's crust. It works, but it is super slow.
Next, we have convection. Now, pay attention, because this is the superstar of our story. Convection is heat moving through a fluid. Hotter stuff gets less dense and it rises. Then it cools off, gets denser, and sinks back down. This constant churning, this circulation, is the main way heat moves through the Earth's massive, gooey mantle.
And finally, there's radiation. This is heat that travels as waves, even through the vacuum of space. It's how the sun's warmth reaches us, so it's super important for heating the surface of our planet. But it's not the main character in our story about the Earth's interior.
And this right here is the perfect analogy. You see that pot of boiling water on the left? That churning motion? That is exactly what's happening inside the Earth, just on a scale that's almost impossible to imagine. These huge slow-motion convection currents in the mantle act like a giant conveyor belt, dragging the continents around on the surface.
Okay, so we've got our fuel, heat. But heat doesn't just do whatever it wants. It has to follow a very strict set of cosmic rules. And that's where we find the blueprint for our engine, the laws of thermodynamics.
Just think about a cup of coffee. You leave it on your desk and it gets cold, right? It always gets cold. It never, ever just sucks heat out of the cool air and starts warming itself up again. Of course not. That simple observation is the core of the second law of thermodynamics. Heat naturally flows in one direction, from hot to cold.
Now, for our planet's story, two of these rules are just absolutely essential. First, the first law says you can't create or destroy energy, you can only change its form or move it. And the second law, our coffee rule, says that heat will always flow from a hotter place to a colder place by itself. These aren't suggestions, they're the non-negotiable operating manual for the entire universe, including our planet.
And this is where it all clicks. The Earth has a ton of heat trapped in its core. The first law says that energy has to go somewhere. It can't just disappear. The second law says it can only go one way, outwards, from the scorching hot core toward the cold of space. This unstoppable, one-way journey of escaping heat is the ultimate force that drives every earthquake, every volcano, and builds every mountain range on Earth.
So let's connect all the dots. We've got the fuel, which is heat. We've got the rules, which is thermodynamics. Now let's see what actually happens when this machine gets going right where those tectonic plates meet.
So in places where those big convection currents are rising up and spreading apart, they literally rip the Earth's crust open. This is called a divergent boundary. Hot magma from the mantle rises to fill the gap, cools down, and creates brand new ocean floor. The planet is literally making new skin for itself along these seams, like the mid-Atlantic ridge.
Now, the Earth isn't getting any bigger, so if you're making new crust somewhere, you have to get rid of old crust somewhere else. It's the ultimate recycling program. This happens at convergent boundaries, where one plate dives under another. The sinking part of the convection current drags that old, cold crust back down into the mantle to be melted again, fueling chains of volcanoes and pushing up massive mountains in the process.
And then there's the third type of boundary. Sometimes the plates aren't pulling apart or crashing together, they're just sliding past each other horizontally. But it's not a smooth ride. The jagged edges lock up, building up incredible amounts of stress for hundreds of years, until finally, snap, the rock breaks, releasing all that pent-up energy in an instant. And that right there is an earthquake.
Okay, I know what you might be thinking. This is a great story. It connects heat to volcanoes. It all sounds very neat. But how do we actually know any of this is true? We can't drill thousands of kilometers into the Earth, so how do we get the proof?
Well, amazingly, we use the earthquakes themselves to give the planet an ultrasound. See, quakes send out different kinds of energy waves. The two we care about are P waves and S waves. P waves are compressional, kind of like sound waves, and they can travel through pretty much anything: solids, liquids, gases. But S waves are different. They're shear waves, and here's the absolute key: they cannot travel through liquids. They just stop.
So, after a big earthquake, scientists with seismographs all over the world listen for these waves to arrive. And they noticed something really strange. No matter where an earthquake happened, there was always this huge shadow zone on the opposite side of the planet where the S waves just never showed up. They would completely vanish.
And that was the brilliant aha moment. The missing waves are the evidence. The only way you can have a massive shadow where S waves don't appear is if they hit something on their journey that they couldn't get through, a giant ball of liquid. That's how we discovered that the Earth's outer core is molten metal. It was the final, undeniable proof that our planet is powered by a liquid-hot engine, all governed by the laws of heat. So, from a simple cup of cooling coffee to the liquid heart of our world, the laws of thermodynamics are in charge. It's a process that's been going on for billions of years, and it's not stopping anytime soon. Which really makes you wonder, as our planet continues to slowly cool, what will the surface look like in another 250 million years? What new continents will form? The engine is still running, and we're all just along for the ride.